All right, so far we've talked about several different types of action spaces, right? So the hypothesis space has a bunch of decision functions. Every decision function takes an input from our input space and gives an output in our action space. And the action spaces we've talked about so far are what? Real line for regression, -1, 1 for hard classification. Last week we talked about multiclass. So action space was 1 through k, right? We labeled them with numbers, but basically elements of a discrete set, finite set. Okay, and we even at the end spoke about, well, as an instance of multiclass, but multiclass where the number of classes is huge. This scenario where you need to use structure in the output in the output classes to choose from a potentially exponentially large set of classes. All right, so those are the action spaces we've talked about so far. Today we're introducing a new action space, which is probability distributions on the output. So suppose we're doing multiclass. So rather than outputting a single class, we'll output a probability distribution over the set of classes. We actually did do this once before. When did we do this once before? We have one model that outputs potentially probabilities over a lot of classes. Trees? Yeah, trees, yeah. Because in the leaf node of in each of the leaf nodes of the trees, we can build a kind of a histogram or counts of how many times each class showed up. And when we predict that, that is a probability distribution over classes. So we have talked about it before. But now we're going to hit it more systematically. OK. So as a motivation for doing this sort of thing, I'm going to talk about a project that I actually worked on, or some colleagues and I worked on a few years ago at a startup company. It's called Sense Networks. Started in 2006. And the idea was to be the experts in location data. And we had a first product that was called CitySense in 2008, so a while ago already. And the idea of CitySense was it would be a guide to nightlife in San Francisco. But not like Lonely Planet or not like guided reviews, but an app to tell you in real time where the action was, where people were going. So you're new to the city or you're just going out on the town. You want to know what's hot tonight, typically, and what's unusually popular at that moment. OK. So this was what the app looked like. It gave you like a city map, and then you had these hot spots. And there's two modes. One was like, what's really hot right now, like, or typically at this time, and then what's unusually popular. All right. So, I mean, the data science question here is, how do you decide when something's unusually popular in any moment, right? Yes, please.
Why is it no longer in the
So sad. That's a good question. Not a driver of revenue, and we moved on to other things. All right. OK. So our data set was taxi cabs. We found a taxi cab company that was willing to lease us or sell us their data. They had GPS tracking in every taxi cab. And so you could watch the taxi cabs moving around the city in real time. And so what we used was they also specified the pickup and the drop-off locations of every taxi ride. So we decided to use the drop-off locations of a taxi ride as an indicator that someone was going there. So people don't take taxis in San Francisco as much as they do in New York, but at least this was a proxy. You need to start with some set of data. All right. So the idea was to use it to bootstrap. So what does that mean? So if someone puts the app on their phone and they're using it, in exchange to be able to use the app, they have to agree to share their location data with us. So once they're using it, then we could get location data from the app. All right. So data science, what's the problem? We need to model what typical behavior is, typical number of taxi drop-offs in any zone of the city at different times of the day or days of the week or even seasons of the year you could do. And then we need to look at what's actually happening in real time and figure out what's unusual to see maybe there's an unexpected concert or something. All right. Okay. So that was the first product. The second product is more, actually it is still in the App Store, and it's more New York City focused. It's simpler in some sense. It's to tell you at any given street corner in Manhattan how many cabs you can expect to be picking up people. How many taxi cab pickups can you expect to happen on any street corner in New York City based on the time of day or the day of the week? It's pretty simple. It's still a modeling problem. All right. OK. But we're going to focus on the city sense anomaly detection problem. It's a little bit juicier data science-wise. But just because New York City is more interesting, we're going to look at the New York City taxi data, which we also have, because we live here. You could download it yourself if you're interested. Some 2013 data. OK. All right, so today we're talking about probability models, and in particular, predicting probability distributions as your action. All right, so these are all the things we've discussed so far, all the different action spaces. And today we're going to talk about an action space consisting of probability distributions on Y, on the output space. OK, so why would we want to do that? OK. So here's what it would look like if the output space is, say, reals. So output space of reals would be, what kind of problem is that? It's only, yeah, it's what? Output space is reals, that means it's regression. That's the definition of regression. Regression means the output space are real numbers. What your data has come in with an input x and an output that's a real. Regression. All right, so we're considering a regression problem. And we want to take an input x and output a probability distribution on y given x. Okay, so that's what we produce. We produce the distribution. All right, so what can we do with that distribution? So for instance, suppose we have a loss function that we're actually interested in, something like square loss, typical for regression. If I give you, so I get an x, and then I give back to you a distribution over y, a predicted distribution over y, and I want to make a prediction of a single number that minimizes square loss, what would you do? Say again? Expected value. Great. So if you have the distribution over y, we've done, I think, on problem set 1 that the expected value of that distribution minimizes the square loss in expectation. Great. And what if the loss is L1? Absolute loss. Yeah, median. You take the median of the distribution. So if you have the distribution, you can immediately predict the optimal thing for square loss, the optimal thing for absolute loss. And in fact, any loss function that you want to optimize, you can kind of the most information you can have is this conditional distribution of y given x. OK. All right, so what else can we do with the distribution? All right, so we have the distribution, and suppose we're predicting how many taxi cab pickups there will be. So that's a count, right? And you should remember from some probability classes that one very simple family of distributions for count data is Poisson. Right? So suppose we give our model an x and it outputs Poisson 40. What's a Poisson 40? What's the expected value of a Poisson 40 distribution? 40, right. And it has some, and it gives probability to all integers greater than or equal to 0, right? OK. All right. So we inputted x, and suppose x is specifying a particular region R and a particular time, say between 9 p.m. and 10 p.m. The model returns Poisson 40 as its predicted distribution. All right, so suppose the actual number of taxi pickups in that hour, in that region, is 100. So we can say how unusual that 100 is according to the model. For instance, a standard statistical method is to look at the tail. So we could say, all right, well, 100 that's big. That looks bigger than the average. So how can we quantify how unusual that is? We can look at what's the probability of seeing 100 pickups or more. Kind of a standard statistical approach. You see it in hypothesis testing. So that's probability that y is greater than or equal to 100 given x. And then we could simply sum from 100 to infinity of the probability of y given x. And that's a measure of, according to the model, the probability that we would ever see 100 or more pickups. And we could say, oh, that's really rare. That's like less than 1%. Or we could say, it's not that unusual. All right? So with the predicted distribution, you could do more. You could do things like measuring how anomalous some event is. All right. What else is fun to do? You can get prediction intervals. Same idea. So a prediction interval it's very natural. It's kind of like a confidence interval, but for prediction. So given an input x, I'll say, OK, I think that with 95% probability, and you don't say that for confidence intervals, but you can say this for prediction intervals in this scenario. I think with 95% probability, according to my model, there will be between 50 and 75 taxi pickups. OK, that's a prediction interval. How do you do that? Well, if you have the distribution, it's pretty trivial. You just find two values, a and b, so that the probability that y is between those things according to your predicted distribution is 0.95. So you can do that with quantiles, et cetera. Just so you know, there's another way to do this same thing, something called quantile regression, which is where you use a different loss function. Like instead of, what's the loss function we use to get the 50th percentile? Do you know what the 50th percentile is? There's another name for it. The median. All right. And do you know what loss function we use to get the 50th percentile? Yeah, absolute value. OK. So there's a modification of the absolute value, kind of shifting, kind of angling. That's another loss function that will give you different quantiles instead of the median. So you could use, that's just another approach, unrelated to today's discussion. OK. All right. Let's talk a little bit more about this problem, because since you guys are working on your projects now, this is almost a good opportunity to point out just a few techniques for doing some data analysis. All right, so in our scenario, we have a taxi cab. I think we're talking about pickups instead of drop-offs in this problem. So a taxi cab pickup happens in a particular location at a particular time. So space is continuous. It's latitude, longitude. Right? This is a little bit challenging to deal with. And time is almost continuous. We have it designated in seconds. There's a lot of times. So we bin them up. And so we partition space and time into buckets. And we're calling them grid cells. And so we break up the city of New York into roughly 400,000 grid cells. And the time we break up into hours. All right. So here, for example, is a single grid cell. You know where that is? Penn Station. I wrote it down. OK, so it's about that big, less than a block. There's another view. You can see the taxi cabs lined up there. This is the grid cell in New York which has the most frequent taxi cab pickups. OK, at least at that time. All right, this should be familiar. This is right outside. All right, so that's just to give you an idea of the scale of the grid cells. All right, let's look at a bit of data. So this is, what are we looking at here? A single grid cell, the one by Penn Station. And we're looking at a particular week, 1 week of data. We've plotted the number of taxi pickups in the hour. Let's see. One sec. Yeah. Across the week, Sunday through Saturday. I don't know. One thing to note is like the Saturday pattern is pretty different from Monday through Friday pattern. Saturday and Sunday are different. You can see that Saturday and Sunday don't really have only really one peak, whereas Monday through Friday seem to have these at least 2 peaks, right? You know, people going to work. All right. So what would we want to do? Yeah.
Is this for 1 week only, or is it aggregated
This is 1 week, no aggregation. Yeah, good question. So here's 4 weeks separately plotted. And you can start to see a little bit of the variation from week to week. And it's this variation that we'd want to capture in our distribution, right? So suppose I'm given an x. Let's suppose I'm limiting to a particular grid cell, and someone says, tell me what we can expect for week hour. How about this one, 100 and something. And so we can say, all right, well, what has happened over the last 4 weeks? Well, there's some spread up and down here. So maybe we want a distribution that has at least the right mean and the variance to capture that spread. That's what we're looking for. All right. So here's aggregated over 27 weeks, but not averaged. We've done some box plots, which show the spread and the variation at every single hour across. This is 3 days, Sunday, Monday, Tuesday, across 27 weeks. All right. So here's a better idea of what we want to predict. We want to be able to capture this type of spread. And yeah, we see that the variance changes at different week hours, right? So that would be nice to capture. So that's all part of the distribution. OK. Here's another place. This is Courant. This is a single week. And you can see that most hours have 0 pickups. Sometimes there's 2. It's very discrete. We get up to a maximum of 2 pickups in an hour for this particular week. All right. Here's Sunday through, OK, now here's aggregated over 27 weeks, the average. Not average. What is this? This is the box plot. So this is the distribution of number of pickups by hour. And you can still see that 0 is very common, and then sometimes we get up to 2, 5. All right, so that's Courant. So distributions with quite different characters. So maybe these distributions, I don't know, maybe you can model it as kind of a, roughly it's like a Gaussian with different variance at different places, different mean and different variance at different points. Maybe. But here, no way. It's all discrete. It's all 0s and 1s and 2s. A Gaussian wouldn't really capture this very well at all. OK. Maybe Poisson would be good. All right, so the prediction problem, a little bit more spelled out in this case. So somebody queries a grid cell and a week hour, and we want to tell them what to expect. We want to produce a distribution. OK, so about 400,000 grid cells. There are 168 week hours in a week. So that's the input. You could imagine at some point adding more features, not just week hour and location, but also, is it a holiday? Is it raining? Is there special events? These sorts of things. Or recent history. Okay. And the action space is the distribution on pickups. And then we can observe an actual number of pickup. It's a count. OK. And one question we're going to come back to is, we predict the distribution. How do we know how good the prediction was? Right? What's our loss function for measuring the quality of a predicted distribution? OK. So this is the data. This is what label training data would look like. Grid cell week hour and the count that was observed. OK. So later today we're going to discuss how to evaluate. But how do we even set up the problem? What would be a good way to split this data into training and test? I have about 50 weeks of observed data. And that's what the data look like. Also, each data is timestamped. Each row, say, is timestamped, so I know when it occurred. So the standard thing when you want to split into training and test is, random, right? It's very important to do things randomly. But that might not be a good idea here. What do you guys think?
Should be IID.
What should be IID? Oh, OK. I'm not sure. OK, so, and you're worried that it's not because things change over time?
Yeah.
No, this is OK. No, this is standard, actually, because in a problem where you get input and output, you have different outputs for different inputs. So they are IID from a distribution on X cross Y. That's OK. OK, but maybe I do have some worry about IID, but I'm not. Maybe it's the sense you meant, but I'm not sure if it's what you meant. OK, yes. Chronological. So what do you have in mind as a potential issue?
Because when you have to tell the user how many paths that you expect, you only have past data. So you shouldn't train on future data for a current prediction.
Right. So to capture what you've said, when we actually apply this model, the scenario is we have all the data we've seen up to right now, and we can predict, and we have to predict on what's happening next. So when we kind of simulate this by separating to train and test, we need to make sure to only train on data that happened up to a certain point. Well, certainly we need to make sure our examples only look at things that happened up until that moment we're making the prediction. But would it be so bad to take something as training, something later in time? What's the issue of?
If all your data is stable from the last week, then it's going to be skewed because you're not going to see all the stuff before. Or conversely, if it's all from the very first week in your data set, then it's not going to represent the future.
Right. So you're concerned about differences between weeks. Yeah, I'm also concerned about differences between weeks. So there may be trends throughout the course of the year, right? There's seasonality. Maybe more people take cabs in the winter than the summer. Maybe vice versa. I don't even know. Maybe, there are other kind of things that are not stationary over the course of a year. So to be safer, and because in practice, when you actually run this model, you didn't get to train on anything that happened in the future, right? You only trained on things that happened in the past. So when you want to split your train and make your train and test set, it stands to reason that your training set shouldn't be kind of everything up to a certain point, and your test set should be after that point. So you should do you should split in time your training and test set. OK. Yeah, and this is, please.
Yeah, so I was going to also say seasonality, and so I'm wondering, would it be better to have at least 52 weeks and then maybe do some sort of weighted average where the more recent weeks are much more important? Or would it be better to train on just last week?
Yeah, great question. So, all right, so far I'm only talking about training one model. So, but if you were willing to build a new model every week, then it does make sense to me to weigh more heavily what happened more recently. Yeah. OK. All right. Let's talk about stratification a bit. So full stratification. This means we are the minimal unit that we talked about in terms of kind of collecting our data together was the grid cell and the hour. So that's as far as I'm concerned right now, that's full stratification. Stratification is breaking your data up into chunks. OK. So what are we looking at here? On the x-axis is counts for the number of pickups from Courant on Tuesdays between 7 and 8 p.m. OK? So let's start with the white histogram or the white bar chart. So this is from the test set. This is how many counts were observed, how many kind of days or Tuesdays between 7 and 8 p.m. that had, in this case, 0 pickups. This is 1 pickup, 2 pickup, 3 pickup, et cetera. All right? So this is empirically over the course of, I don't know if this is 27 weeks, how many of each number of these counts. This is the distribution of how many pickups there were at this time at this place. That's the white stuff. That's on the test set. So we had a similar table on training set, from training set. And we fit those with 3 different models. Poisson, negative binomial, and histogram estimator, which just does counts. And so you can see the various fits. OK, so just to make sure you guys know what I'm talking about, So I build a model, and as input, I say current Tuesday between 7 and 8 p.m., what would the output be like? Say? OK. So each of these curves is like the output of my model, because each of these curves is a probability distribution on the number of counts. OK? So yeah.
And this is built only on the data for that grid location that time?
Yeah, this is data built only on current between 7 and 8 p.m. on Tuesday. So we just looked at that data. That's right. And you can imagine we built a model for every single grid cell for every single hour of the week. So that's 400,000 times 168 separate models. Okay? One for each input X.
You're not allowed to like use other grid cells to predict like grid cells. You can't be like, oh, uptown is really empty, maybe downtown's full, and you're creating a separate model for each cell. Is that correct?
So it's certainly correct that in this way I described, we're not doing that at all. But that's because this is called full stratification. Full stratification means literally that we're building, well, in stratification, we build a separate model for every stratum, every piece that we broke the data into. And full stratification means we're not combining things at all. Yeah?
Is it possible to add in your model, besides the location and the time, just add the data of the past hour? So if you know, like, you would predict like 5K, but if you notice that past hour you had like 20 pickup, maybe something is going on and you're still going to predict that high count.
Sure, sure. You can certainly convert this into more of a time series model where you have recent history and you have the model trying to predict what's happening next based on recent history and historical data. Yeah, that would be another type of model. In this case, we couldn't do this because we didn't have recent history, this data set. So we had a fixed data set from 2013, and that was that. Yeah?
What if instead of creating a model, you just estimated the distribution in the training set?
What do you mean by estimate the distribution? And how would you estimate the distribution? So, OK, so I give you, the data would look very much like this histogram from the training set. This would be the actual counts. Is that what you mean?
Yeah.
OK, that is exactly what red line is, histogram estimator. That's exactly what that is.
So that is a model. You are considering that a model.
Yeah, I consider that a model. Yeah.
Why does the red line not match the histogram?
Well, that's a good question. So the red line was trained on training set, which was the first 14 weeks, and the white bar graph is the result of the following 13 weeks. So what we're seeing here is some change. Yeah, some non-stationarity in the data, which means things change over time. Yeah. Yeah.
So are the white bars the prediction of the model, or they're real
Nope.
outcome?
Why? OK. So Y bar, the Y bars are the histogram of what was actually observed in the test data. Yeah. OK. All right. So this is a little definition of stratifying. It's breaking our input space into groups, and we treat each group separately. We build a separate model for each group. No information sharing across groups. That's stratification. Kind of the opposite of stratification is called bucketing or binning, where you take different subsets of data and you combine them. So this would be, for example, saying, well, the grid cell at current is right next to the other grid cell at current, and we don't have much data for either of those grid cells. What if we combine those grid cells together when we make our model? Then we have more data for that area. Okay, that would be bucketing. All right. So in terms of bias and variance, would bucketing increase or decrease the variance? Bucketing would decrease the variance. Bucketing essentially increases the amount of data you have, which would decrease your variance. And what about bias? Bias would increase. Why would bias increase? It's because you know, this one grid cell here for Courant northeast corner has maybe a slightly different characteristic than the one right next to it, right? But when you put them together, you're kind of biasing your output towards the average of the two. So you're pulling it away from what it really is towards something else. That's kind of a general notion of bias.
What do you mean what it really is?
Say again?
What do you mean what it really is?
What it really is. So, well, if you imagined like a model that actually determined how many counts were going to happen, then that unknown like mean number of counts or something is what it really is. So this is just a, yeah, fair question. Should I give more of an answer, or is that enough just to acknowledge that that's a good point? OK. Well, look at it this way. Suppose you observe these street corners for like 10 years. OK? And that's what you really want to know. You would like to know the 10-year average number of pickups at the street corner. That's what you wish you knew. But unfortunately, you only observed it for 7 weeks. OK? So the true number is the 10-year average, and your observation is 7 weeks. So that's what I meant by the true, like that would be a way to think about the true number. Now, suppose the 10-year average for this grid cell is 10 pickups, and the 10-year average for this grid cell is 8 pickups per hour. OK, so when we pool the two things, the two grid cells, what's the expected number of pickups that we're going to have? 9 per grid cell. So we're biasing towards 9. OK. OK. So suppose we look at the data and we're like, oh, all the weekdays look pretty much the same. Why don't we just combine the weekdays? So that's a bucketing. So here we're combining Monday through Friday, 7 to 8 p.m. All right, let's go a little faster here. Then you could also say, oh, 6 to 7 p.m. looks kind of like 7 to 8 p.m. Combine those. It's just a bias variance trade-off. Get more data, decrease variance, increase the bias. OK. All right. So this is getting this is kind of the same thing we're talking about, but at Penn Station. And you could see that the test distribution is much different from the distribution learned from the training. So this is a big, something happened here. Something changed. This would be like, need to investigate that. Maybe someone got the timestamps wrong or didn't account for daylight savings or something. OK. OK. So far we're talking about bucketing and stratifying as our mechanisms to trade off between bias and variance. But all the modeling that we've done so far, they're trading off between bias and variance all the time. What are different ways that we trade off between bias and variance with our modeling tools? Suppose, for instance, ridge regression. Regularization term is essentially trading off bias and variance. What are we biasing towards with ridge regression? Yeah? What are we biasing towards?
Small code.
Yeah, towards 0 for the parameter values, right? We're penalizing anything moving away that's non-zero. We're pulling things towards 0. So in our ridge regression, we're biasing towards 0 would be a way to say it, or shrinking towards 0, people also say. All right, adding more features. Adding more features can potentially should decrease bias, but may increase variance in a certain sense, because it's harder to estimate more features. But then you correct that by regularizing more. So, OK. But the point is, there are other ways to do bias and variance besides this rather coarse stratification or bucketing. So the question is, can we use our modeling tools to do this bias variance trade-off for predicting probability distributions? OK. So we can. One sec. Okay. Questions? Yes.
So I get like if you bucket time frames that like use increased bias, but if you bucketed like grid cells and then you just kept those larger grid cells and predicted those, would you actually both decrease bias and variance? Because now you just have kind of like a larger area that you're trying to predict.
Okay, so so the question is, would you really be decreasing bias if you merge two grid cells together? So, and what you're saying is, well, what if I also change the problem so that my input is just the bigger grid cell?
Well, what's the point of bucketing otherwise? Just to kind of have more.
To decrease variance. That's right. So the idea is that, these two inputs are different, but I just don't have enough data to get good enough estimates for each of the separate grid cells. So to even have a hope, I'm going to need to merge them together. And to get,
They are equal.
well, I may know that they're not really equal, but I may say like, they're close enough. Yeah. Like for example, suppose we're in scenarios where a lot of your grid cells have 0 counts, right? And then 1 out of 10 has a count. So has an arrival. So if they're all exactly the same, the average is 1/10 expected number of pickups per. But if you don't pool, then you're going to predict 0 for every single one. You have no idea like a distribution besides 0.
You could use a kernel.
Say again?
You could use a kernel
What kind of kernel? What do you mean?
to get information from the neighbor bucket.
Ah, okay. So not a kernel in the sense that we've spoken about, but in the sense of kind of your prediction at a given point is some weighted combination of what's going on around you. Okay. Yeah, oh, I guess you could use RBF kernels in that sense. Yep, different ways. And that would be like a model that we're getting towards, exactly. Yeah. Yeah.
Are there any like time series analysis tools you can use to like smooth out the trend before you apply these techniques?
Smooth out the trend?
Yeah, like time trend, because we assume there would be like some time trend embedded in data.
Can you say again some time trend?
I assume there would be some like natural growth, like time trend.
Oh, okay.
In data. So I was wondering, is there like time series analysis tools you can use to like smooth out the trend before you apply these?
Okay. So, right. So our approach here was to model every week hour separately. And you're pointing out, okay, but what if there's like a longer term trend over time? How are we accounting for that? And if your model is too weak to account for that, maybe we can do some correction before we even start and get rid of the trend. So yeah, you could, for instance, I mean, there's standard time series ways to do that. There's like trend, seasonality, and kind of recent history are like the standard 3 things that go into a basic time series model. So you could extract the trend, maybe the seasonality too, with the initial fit. That could be a good pre-processing step. Some more questions?
Is that the best practice for training test split on time series data?
I mean, you have to use common sense. You mean to split chronologically? Yeah, you have to use common sense, and what guides that common sense is how you're actually going to use it. And you need to make sure that the way you set up your train and your test resembles as closely as possible what's going to happen when you actually deploy. Yeah. Yeah.
Can you, instead of like bucketing, do the other way around? Maybe have like a big square of Manhattan and then start doing kind of what we did with decision trees and start like partitioning and then trends.
Okay, so it sounds it sounds like you want to dynamically break things up.
I'm thinking about not having a lot of bias because I don't know, like you may have a square where half of it is like kind of safe and then the other half is like very dangerous. So you could have a lot of bias within a square. So
Okay.
thinking of, I don't know.
So maybe the question is there a way to choose your buckets in a way that minimizes bias so that you guess you look at the data and you're like, oh, these things look pretty close. Let's assume they are close. These things definitely aren't the same. Let's make sure they don't go together.
Well, I guess
Computational, that went outside the scope of what I'm thinking about right now. I just want to find something that works as a good model. So okay.
Is that more like stratification instead of bucketing, like start with a bigger picture and then decrease instead of start with smaller and increase?
Oh, okay. So I guess it's just two sides of the same thing. At the end of the day, you're going to end up with a partition of the data, or the partition of New York into different spaces. And the only question is how you get to that partition. Okay. Okay, you can ask more later. All right, so we have a few minutes before our break, but let's get started. Do you guys want to take a break, or now or in 10 minutes? What? All right, fine, break now. One opinion rules. If anyone wants their tests back, I brought them again today. All right. Some people are asking about homework 6 extension. I don't care, actually, when the due date is for homework 6. It can be whenever you want. However, we can only release the answers after it's due, right? So if you want to see the solutions, we're happy to talk about the solutions, but there's only so much time. If you want to actually see the solutions before the test, it'll have to be due, I guess, Monday. So I don't know. If you guys want to post a poll or something, that's fine. But that's the situation. How are you guys doing with homework 6 if you've taken a look so far? Medium. Okay. Okay. You guys know about maximum likelihood estimation? All right, we haven't talked about that yet, but we're talking about it now. So, talking about probability distributions on Y, on the output space Y. It's unknown, we want to estimate it. Let's assume it's either a probability mass function or a probability density function. And so the typical Y's we've talked about. All right. So my favorite part of learning theory, machine learning, is evaluation. It's figuring out how to evaluate what you've produced. I think that's the most important part, because you can't really get anywhere until you know how to evaluate what you've come up with. So someone gives you a probability distribution estimate. Let's write that p hat, right? That's what your model produces. I predict this distribution for the number of taxi cab arrivals. How can we evaluate how good it is? That's the question facing us. Okay. So we want this p hat to be descriptive of future data. If we want to actually use it in the wild, that's part of the point. It's got to be useful. It's got to predict what happens next. So standard way to think about this is to define what they call the likelihood for a predicted distribution. So suppose we have some data sampled from the true distribution py. Okay? The likelihood of p hat, this is a predicted distribution. So we say the likelihood of p hat for the data d that we observed is defined to be like this. What is this? This is an expression for the probability or probability density assigned to the data d in our sample. So we have n IID samples. By independence, it factorizes into the p hat probability of each of the things that we've observed. So this is the likelihood of p hat for the data d. Okay. So we've produced our p hat. We get a fresh sample d, and we evaluate the likelihood, and we hope that it's really big. And if we have a lot of models we're comparing, we're going to like the one best that gives the highest likelihood to the new data. Right? That's evaluation. Is that clear? Any questions on that? Straightforward. So here's some notation. We can write L sub d for the likelihood. So p hat is in the parentheses the way people prefer it to be spoken about is the likelihood of the model for the data instead of the likelihood of the data. Could get into why some other time. Okay. So that's the likelihood. And you can imagine you could use the same idea for fitting, right? If you're trying to, you could try to fit your model to maximize the likelihood on some training data. That's actually maximum likelihood estimation. But first and foremost, that's how we can assess how what fits new data. All right. So we're going to be dealing with parametric probability models. You can imagine your model producing non-parametric things, like a histogram. But we're going to deal with parametric models. And so parametric model, it's a set of probability distributions that we'll write like this, py. And every distribution is kind of indexed by a parameter setting theta. Theta comes from some parameter space. OK. So in probabilistic modeling, analysis usually starts with something like this. We say, suppose the data is generated by a distribution, by some distribution in this specific parametric family. Then the next step is, OK, let's figure out which one it is. So that's a way to frame the problem. And there, what you know you're doing is you're saying, well, I know the world isn't really quite like this parametric distribution, but for my purposes, I'll approximate it that way. And so I'll assume that the data is generated from something in the family and work accordingly. So we're not going to say that. The results may be similar, but we're not going to say that. We're going to look at it a little bit differently. So from our perspective, what this parametric model is, we're thinking of it as, did I write it down here? I didn't, so I can ask. So of all the spaces we have, where does the parametric model fit in? I consider it, it's one of our spaces that we've discussed. Could be one of two, actually. Is it an input space? Output space? Action space? It's a function space. That's pretty generic. It's a space of parameters, of distributions. All right. So if we're trying to fit some data with a single probability model, then what we're producing is the probability model. So if the input is, so in the case of the pickup predictions, if our input is an x and the output is an element of a probability distribution from a parametric family, then it would make sense to call this parametric model a action space, because we're producing something as our decision function is producing a parametric model from the model space. OK. On the other hand, we could, if we don't have any input and we're just trying to fit some data, right, with a distribution that fits it as well as possible, then that's all we're producing. So you could think of it as pulling a distribution from a hypothesis space. So then you could think of this parametric model as a hypothesis space. All right. All right, so just to get you thinking about parametric models, I just put some slides on a few to remind you. There's the Poisson family, which gives distribution for counts, so 0, 1, up to infinity. It has one parameter. You could call it lambda. That's typically taken to be the mean of the Poisson. There's the beta family, which is supported on the interval 0, 1. It's got two parameters. You kind of have something that you can control both the mean and the variance, so where it's centered and how far apart things are spread. Gamma family, supported on the interval 0 to infinity. Can again control the mean and the variance. OK. So we have some parametric families to keep in mind. All right. So maximum likelihood estimation. Suppose we have a parametric model, and we have a sample D. Whoops. We're going to define the maximum likelihood estimator for theta in this model as the theta hat that maximizes the likelihood of theta given D. All right. So the likelihood is the probability or probability density of the observed data for the distribution corresponding to the parameter theta from the model. because we assume the data is IID, it would factorize into the probability of each individual point. Just standard stuff. Okay. So in practice, we often, if we're trying to maximize this product, it's equivalent to maximize the log, because the log of a product splits nicely into sum of the logs. So often this bottom expression is easier to maximize by gradient, taking the gradient or something like this. Okay. So maximum likelihood estimation is finding the theta that maximizes this log likelihood of the data, or the likelihood of the data. And we can, so the likelihood is a function. It's a function of theta. The log likelihood is a function of theta. As we vary the parameter, the likelihood that we get for the data will increase or decrease. And in maximum likelihood, we want to try and find the theta that gives the greatest likelihood for that data, that has the greatest likelihood for the given data. All right. So it's an optimization problem. And sometimes we can find a closed form solution, like for Gaussian, maximum likelihood with Gaussian distributions, you can just use calculus to find the maximum likelihood estimates. Or sometimes you just need to use numerical methods, like we know, stochastic gradient descent or Newton's method, gradient descent, lots of choices. In a week or two, or in a couple more lectures, we'll talk about EM algorithm, which is another method to try to get to the maximum likelihood in more complicated situations. But here's an important point to bear in mind. The maximum likelihood doesn't always exist, but a lot of times there's a good reason for it. So I just want to give you a couple, at least one example to bear in mind. Bless you. So let's consider a Gaussian family of distributions. So univariate, it's Gaussians on reals. So we have mean and variance, 2 parameters to fit. And suppose we have a single observation y. Say y is 10. So what would you think the maximum likelihood mean would be? Well, 10. So the observation is 10. And so the maximum likelihood mean would be 10. That's right. And what would the maximum likelihood variance be? 0. Right. So the issue is and what's the likelihood when we put the variance to 0? Well, not quite. So here's our data. So we have a data point at 10. So suppose this is, I don't know, this is variance, this is standard deviation, I don't know, 2. OK. So the likelihood of the observation 10 under this distribution is whatever this number is. This is the likelihood scale. All right. So if we decrease the standard deviation, we have to have the area under this curve stay at 1. So shrinking it in standard deviation makes it more pointy. Okay. So this is the likelihood with the smaller variance, smaller standard deviation. And as the standard deviation decreases to 0, the likelihood at the point 10 goes up towards infinity. So there really is no maximum likelihood because you cannot have variance of 0. It's not really a distribution. So someone who said 0 was also not right, but not wrong, because there is really no distribution with variance 0. You could say, oh, it just puts all its weight at 10. OK, but that's not actually a Gaussian distribution. Okay. Kind of more a limit of Gaussian distributions. OK, so you have to be careful with maximum likelihood. Doesn't always exist. That's an easy example. All right. Let's work one. So we'll at least look at maximum likelihood for Poisson, just as a basis that we'll refer back to. You guys have probably worked this out in another class at some point. Fitting Poisson distributions, for example. Maximum likelihood? Yeah. Good. All right, so you should recall the Poisson log likelihood for a single observation. This is the probability mass function. Which of these is the parameter? We have k and lambda floating around, and e. Which is the parameter? Lambda is the parameter. It's the expected number of counts. It's the mean. And the kind of variable is k. OK, so this is an expression for that probability mass function. This is the probability of a count of k for a Poisson lambda distribution. And that's for a single observation k. If we have multiple observations, we just, by independence, multiply these numbers together to get the probability of all of those. And we can take the log, and it comes out to this summation. Splits up nicely into a sum. And then to fit the model, we would just maximize this expression with respect to lambda. Could probably solve for that exactly with some differential calculus. No problem. All right? OK. So lambda is the average number of counts. Good, because it's the expected value. That makes sense. OK. So this is a little bit of a flashback to the taxi cab pickups. So now we have this notion of log likelihood as a measure of how well fitting our predicted distributions are. So on that data set for Penn Station, where we make predictions using histogram model and negative binomial and Poisson. So on the right, I've computed the test log likelihood for each of these models. So the average log likelihood of all the predictions made. And it's a way to assess numerically different models on test. Okay. So the question is, what does it mean to have a log likelihood of negative 200? OK, good question. So a likelihood basically comes in two flavors. Sometimes a likelihood is just another word for probability. When would that be the case? Yeah, when we're dealing with probability mass functions, and we're actually maximizing the probability of something. For something like Gaussian, where we'd have densities, and we're trying to maximize, when we say maximum likelihood for something with a continuous distribution, we're really, the y-axis here is, it's not in units we interpret easily. It's, I don't know, units of density or something. When you integrate, it equals 1. So likelihood is not something that you can interpret in an absolute sense unless it's a probability. Otherwise, it's just a likelihood. So if this were a probability, are these related to probabilities, or are these not in this scenario? Say again?
Log of the probability?
No, I mean, yeah. So do you think this is when I say log likelihood, is this actually log probability? Yeah, it is, because we are just predicting discrete things that have actual probabilities. So how can we go from this number to a probability? Take e to this number. So what happens when you take e to these numbers? Super small. Yeah, OK. Why are they super small? Because every observation, may have had a certain probability. Like, oh, we had 10 counts. My probability in this particular moment, my predicted probability of getting 10 counts was 1/10. So it's small, but not really small. But now we have, I don't know. I don't remember what I'm aggregating over, but say like 27, no, it must be more than that. So there's like 1,000 observations, each with predicted probabilities of like, around 1/10 or something, or 1/5 or 100th. And you multiply all those together, you get a really small number. So that's why your log likelihoods are often negative and in that kind of a range. Yeah. So we could have also got, this was total log likelihood, but it would also make sense to get average log likelihood, which would make the numbers more on a scale we're used to. Say again? Yeah, we want it to be as large as possible. So which would be the best here? Negative binomial is the best, yeah. Some questions? Yeah.
Is there any limitation about the probability solution, like the model that we want to use, like log likelihood for? So, for example, we could use like SSE, just like
What's SSE?
Error, you know, like.
Oh, sum of squares error.
Right. But
Uh-huh.
since this is like a probability model, we want to use likelihood to find the best model, basically.
Correct.
But is there any limitation on the model? Model should be parametric, or does it work for all models, like Gaussian, but like Poisson, any different model?
Great question. So we're safe with a parametric probability model for sure. And non-parametric probability models, you're always safe to evaluate the performance on tests using likelihood. That's fine. You just always need to be careful on how you fit your models. Sometimes maximum likelihood on a huge hypothesis space may overfit. So a non-parametric model that can fit almost everything may not work very well, but you can still assess how well it does on tests using likelihood. I think likelihood is quite universal as a way to test probabilistic predictions. Yeah?
Is there a simple example of a non-parametric probability model?
You want a simple example? Sure. The simplest example I could think of is where I get a bunch of data points, and my predicted probability model, suppose I have n data points, my predicted probability model puts discrete mass of weight 1 over n on each point I've observed. Is that clear?
Isn't that just uniform?
It's uniform on the points that I observed. But suppose I'm sampling points from a Gaussian distribution, and I get, suppose my data actually come from a Gaussian distribution. Imagine that. And my points are observed there, 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 and there. A non-parametric model would be, for instance, to put a weight 1. I don't know if you've seen these arrows indicating like point masses. So 1, 2, 3, 4. Uniform on these at these 4 points. That would be a non-parametric probability model. A silly one, but this demonstrates overfitting very clearly, right? So suppose we have a test set now, and drawn from the same distribution. So maybe the points are here, here, here. What's our likelihood on test? 0. What's our log likelihood on test? Negative infinity. OK. That's what happened here. So notice histogram got negative infinity. So what's going on there? Your second, this is not non-parametric, but. So if we fix the number of bins, it's not parametric, but. OK, so this histogram is another thing we could predict as a predicted distribution. So what happens if we, so this is based on training data like this. OK. Now in tests, suppose we have a point here. What's its likelihood under the model? 0. So no matter how well it fits everywhere else, it doesn't matter because one of those things has probability 0, so the entire data set has probability 0 according to the model. So log likelihood, negative infinity. No good. Good questions. What else? OK. All right, so what I now want to do is frame this probability modeling thing in our usual statistical framework of well, not input space, but output space and hypothesis spaces and action spaces. So output space Y, action space, what we're trying to produce here is probability density functions on Y. All right. So now we want to come up with a loss function. We want to go back to our old framework of loss functions and empirical risk and that sort of thing. So we need to come up with a loss function that encodes the idea of high likelihood is good. So what might be a possibility for a loss function? Or in the direction? Well, yeah? So we know the likelihood is good. Loss function is bad. Maybe like something like negative likelihood or 1 over likelihood or all these, we want to just invert it because a loss is kind of the opposite of likelihood. Loss is bad, likelihood's good. All right, so what you can do is define the loss as the negative log likelihood. So a loss function takes an action, takes something we produce, and an actual output y. So here's a great example where the action space is completely different from the output space. Right? We're producing something that's a probability distribution. That's our action space. What actually happens in the world is something from the output space y, which could be like a number of counts or something. So we need a loss function that takes a distribution and evaluates how good that distribution is for the observed output y, which would be like a count. So one possibility is the negative log likelihood given to that observation under the p that we predict. There's one thing that's changed here that may be a little confusing. I'm sorry for this, which is that the lowercase p here is something that we're predicting. P is not a true distribution. P is a distribution that we're predicting now. So before I was saying that was p hat, but now it's p. Okay. Sorry about that. So log p of y, that would be the log likelihood, negative log py, negative log likelihood. So we want this to be small because we want log likelihood to be big. Okay. All right. So, all right, that's our loss function. Now we could talk about the risk and the risk minimizer. So if the true distribution is q, okay, so the true distribution is q, and we predict our predicted distribution is p, then the risk of p is the expected loss. That's the expected negative log probability or likelihood of y, where y is distributed as q. And similarly, we have the empirical version of that, where instead of expectation, we're doing the sum over the data. Just move the negative outside the sum. And this is exactly the negative log likelihood of p for the data d. So we formulated what we began as looking at the likelihood and was talking about maximizing the likelihood. We can reframe it as minimizing the negative log likelihood, and now it's in our usual kind of empirical risk framework. Okay. All right. So we already discussed how MLE can overfit. Different probability models, hypothesis spaces. And then how do we judge which hypothesis space works the best? So our unifying, it's really clear how to test probability models. If you like likelihood, you just look at the likelihood of the test data under your predicted model. Okay. All right, so this stuff was about kind of fitting data with a probability model, but there's no input. It was just we have some data and we want to fit it with Poisson or fit it with Gaussian. But the problem we framed originally with the predicting number of pickups, we had an input too, which was like location or time. So that's our input space, x. So now we want to move from just fitting a model where there's kind of just an output space, no input space, to an input-output setting. So it's called generalized regression. where the input is some x in a space. Sorry, that should be lowercase. And the output is a probability distribution of y given x. Okay. So we're going to use parametric families to represent the distribution we predict. So here's some examples just to give you an idea of the scope. So logistic regression and probit regression are both instances of this framework. So in those cases, we're always predicting some kind of distribution on two classes. So that's a Bernoulli distribution. Poisson regression. Poisson regression is a special case where we're predicting a Poisson distribution. Linear regression, in fact, turns out to be a special case where we're predicting, you could look at it as predicting Gaussian distributions with a fixed variance. I think you talked about this in section in lab. Yeah? Yeah. Generalized linear models. Another special case that all of these four fit into the generalized linear model framework. A lot of times, if you're looking to do these things in a software package, you just look for a generalized linear model, and each of these will be an option. Generalized additive models. We won't talk about that in this class, but it's related to boosting. You could see it as connected to boosting. Excuse me. And also these gradient boosting machines, they're agnostic as to your loss function. So if you use a loss function that corresponds to a likelihood, then it's also an instance of this stuff. Okay. And what's the big picture here? We have some input, and we're producing an element of a distribution from a parametric family of distributions. That's the common theme of all these things. The first 5 all are linear in a particular sense, and the last 2 are nonlinear. Okay. All right, so we have input and output. Now we have input-output pairs that are assumed to be IID from a distribution, just as usual. Well, okay. Action spaces are densities, or distributions. So now our hypothesis space is a decision function. Now our hypothesis space consists of decision functions that take an input x and produce a distribution y. All right? So that's interesting. So we got a bunch of data, and when we need to find from our hypothesis space a prediction function that will take as input an x and output a distribution. It's a little bit more complicated of an object than we've had before. All right, so the notation gets a little complicated, so let's talk about this for a sec. All right, so suppose f is a decision function. So in regression, f of x is in the prediction, f of x is in reals. For hard classification, it's -1, 1. All right, and for generalized regression, what does f of x produce? This is just repeat what I said a minute ago. It's a distribution. F of x produces a distribution on y. That's what generalized regression is about. Okay. So it's a probability density function or mass function. All right. So f of x is like a PDF or PMF. So we could, if we set p equal to f of x, then we can do things like evaluate p of y. That's a little confusing, right? It's okay, you guys can handle it. So f of x is a density or distribution that we can then evaluate on y. So we could also write it like this. F of x evaluated on y. Or even this, parentheses, parentheses. I've even seen that. Question? Does anyone understand what this means? Say again?
Computer science is it's like lambda because p itself is a function of y, so kind of it looks like a lambda.
Okay. Okay. So that notation you've seen before, parentheses, parentheses. Okay. Cool. All right, so we're going to see this on the next slide. Okay. So the risk of a decision function f. Risk is what is risk? Risk is expected loss. What's our loss? Our loss is negative log likelihood. Okay. So the log likelihood of the prediction. So we get an x and y. Here's our x. Let me do this pointer. Here's our x. We need to get, for that x, our predicted probability. That's f of x. Now for that predicted probability, we need to see how likely it makes the y we actually observed, the output we observed. That's f of xy. So f of xy, that's the probability that our model assigns to the observed y for the given input x. All right? We take the log of it to make it easier to work with. And then we say, all right, well, what's the expected value of a randomly chosen x and y from our distribution of that quantity? So that would be the expected log likelihood. Negative is the negative expected log likelihood. All right. Clear? Well, there's no sum yet. We're doing expected values. This is risk. But once we get to a data set, then exactly there'll be a sum, right? Here, there's your sum. So the empirical risk is exactly the sum over the data of the same thing. Okay. All right. So we need to find an f in our hypothesis space that minimizes this thing, minimizes the empirical risk. Okay. All right. That's the general framework. That's it. That's as far into the general framework as I'm going to go today. And now I can give a few examples. Someone asked about logistic regression, so that'll be our first example. Or Bernoulli regression. Why is it Bernoulli regression? Because the input's at x and the output is a Bernoulli distribution. Bernoulli distribution is great for two classes. So if you want to figure out the probability of a particular class, a 1 versus 0, that's a Bernoulli. All right. So in this part of the field, it's traditional to use 0 and 1 for classes instead of negative 1 and 1, so we're following that. 0, 1. Input is RD. We're going to need a way to parameterize the distribution on 0, 1. Bernoulli is a very standard one. So we'll let theta just be a number. Theta will be our probability that y is equal to 1. All right? So theta is probability of the 1. 1 minus theta will be the 0. Okay. So let's talk about linear probabilistic classifiers. So now I'll tell you where linear fits in. So I want a prediction function that maps from x to theta, where theta represents the probability of the class 1. Theta obviously needs to be between 0 and 1 to be a probability. So here's what the linear method to do this would look like. We start with an x in RD. Then we map it to W transpose x, some linear function of x. That gives us a single number. This is kind of like a score. It's a real number. And then we transform that score into something between 0 and 1 with something called a transfer or inverse link function, f. It's just a function that maps this thing into 0 and 1 that has this kind of name. And we're free to choose an f that we like. That's, you know, different choices of f give different types of models. The probability model then, put all together, is the following. So the predicted probability that y is equal to 1 given x is f of W transpose x. Is that clear? All right. So what can we use for f? Here's some two standard things. The logistic function. You know what the logistic function is? 1 over 1 over 1.
1 over 1 plus e power minus.
Yeah, 1 over 1 plus e to the minus x. It showed up on some other slides. Anyway, that's the red line. And then turns out if you use the normal cumulative distribution function that also has the right properties, that's the blue line. They're a little bit different. If you use the logistic, you get what's called logistic regression. And if you use the normal CDF, which people do in like economics a lot, you get what's called probit regression. In practice, not clear one's really better than the other. Okay. All right, so we'll just write f for now. It's just simpler. So our hypothesis space is the set of functions mapping from x into this f of W transpose t. All right, W now indexes our hypothesis space because every parameter vector W gives us a different function. Is that clear? Do you see why we call this linear? So it's called linear because, in this case, because the inputs x only enter via a linear combination. So the only effect that x can have on the output is via some linear combination of x. All right, so if you want to do something fancier, you have to put those, you have to featureize before this model. So it'd be like W transpose phi of x or something if you wanted to add some nonlinearity on x. All right. Oh, that's interesting. Cool slide bug. All right. So, and how do we choose? We can use maximum likelihood for this setting. So I'll start you off, and then I think it'll be like a simple homework problem to finish it. So we write down a model likelihood for some data. We have x, y pairs sampled. And the likelihood looks like that. Now here's just one clever trick that is useful for binary settings. So this is the probability of yi given xi. What types of values does yi take? 0 or 1. Yeah, 0 or 1, right. F W transpose xi. This is, what probability is this? The predicted probability that y is 1, right. So let's call that theta, right. So if yi is 1, then this expression is what? Theta, or the probability of 1. If yi is 0, no, if yi is 1, what happens to this factor? Yeah, if y is 0, if rather y is 1, this exponent is 0, so this factor is 1. So we're left with just the first piece. So if yi is 1, the thing in this expression is the probability of 1, because that's what FW transpose xi to the 1 is. And if yi is 0, this piece is 1, and we're left with 1 minus that, which is the probability of 0. And that's raised to the first power. So that's the probability of 0. So this is a clever way to write something that's basically, give me the probability of my model assigns to the yi that actually occurred. OK, so that's very useful, because now when you take the log of it, the yi's come down, and this becomes an expression that's easy to work with. And you can solve, I think in this case, you can solve for your parameter directly. Or in any case, you can find the gradient and do stochastic gradient descent or something. So what's the parameter we're trying to maximize against here? Just to make sure you guys are following. Are we trying to maximize or minimize, first of all, this expression? Yes, maximize. On the left, we have the log likelihood. We want to maximize the log likelihood. That's right. And what's the parameter we're maximizing over? W. Yes, exactly. W. Good. Good. OK. All right. So if we find the W that maximizes this expression, that would be a maximum likelihood estimator. OK. So you could also take the minimum if you want to minimize like we usually do. OK. Very good. All right. Any more questions on logistic regression? I fit it into a broader context, but where's that requester? Yeah?
In this case, are there any concerns that you might need regularization or something?
Oh, great question. What about regularization? Answer, yeah, definitely. If you have, for instance, a same situation as in linear regression. If you have, relatively few observations compared to your size of your feature space or your size of your W now, yeah, you're at risk of overfitting. And you can regularize exactly the same way as we regularized ridge regression, although it may be unclear where you put it in. So thanks for asking. So maybe I'll put this in the homework, actually. But the where you'd put it in, OK. So where do you think you would put it in? So let's suppose we're going to regularize with the L2 norm of W. So we're going to penalize lambda times L2 norm of W and put that into our objective function. Which objective function would you want to put it into? This one or this one? The second one. Right. Because this is what we're minimizing. And so if we're going to add a penalty term, a penalty is something you want to minimize. So you add a penalty term to something you want to minimize. Yeah. So you would take this exact expression, and you would add, yeah. There's another way to end up at the same thing in terms of Bayesian statistics with priors and stuff. But that's a topic for either another class or another lecture. Some more questions? All right, let's move on. Let's talk about multinomial, because that fits. It's kind of related, but it fits into what we talked about last week. So multinomial logistic regression is the analog when we have multiple classes. So here we have k classes, and so now we need to produce a distribution on k classes, and that could be represented, for instance, by k numbers that sum to 1 and are greater than or equal to 0. And numbers, these numbers constitute what's called a categorical distribution, or a multi-Newly, which is kind of funny. This maybe should be called multi-Newly logistic regression. But anyway, so for each x, we want to produce a distribution on the k classes. We want to produce these kinds of thetas. So let's spell that out a bit. One way to talk about that is for every x and for every class y. Whoops, that should be k. Sorry. We want to produce a probability theta y. So the probability that we get class that we want to predict class y, the probability that we are assigned to class y for a given x would be theta sub y. OK. So how can we get that into our logistic regression style framework? So now we get x as input, and then we generate this vector of linear combinations of x. So w1 comma x through wk comma x. We have a different w for every class. We're taking the inner product of each of these class-specific w's and our input x. So we have a vector of k numbers that are k different linear combinations of, or linear functions of our input x. So this kind of reminds us of score functions from last week, right? It's like a score for every class for the given input. All right. So each of these numbers can be anything in reals, and we got to map it into probability distribution, into a multi-Newly distribution, into our thetas that add to 1 and are all greater than 0. So the trick for that that's used pretty broadly, it's heavily used in neural networks, and it's classic in statistics too. It's something called the softmax function. It's probably the simplest, one of the simplest things you could think of to do the job. We need to take this vector of numbers and map it to another vector of numbers that add up to 1 and are all non-negative. So check for yourself right now that this has that property. First of all, let's see if they're non-negative. Exponents are always greater than or equal to greater than 0. The denominator is a sum of exponentials. That's greater than 0. So every entry is certainly greater than 0. Now what happens when we add these guys all up? It's 1, because the sum is exactly what we have in the denominator there. So this sums to 1. This transformation is called the softmax. So there. It's a good one to know about. All right. So we get an x. We compute these linear scores for each class. And then we run it through the softmax, and we get a probability vector. OK. All right. So if we put it together, this is kind of what the multinomial logistic regression prediction would look like. So we get an x, and then we say, oh, how about class 1? How about y equals 1? What's the probability you're predicting for class y equals 1? So I plug in 1 for y, and I calculate the thing on the right, and that's my predicted result. So notice we have k parameter vectors, 1 for each class. Remember last week we also started with k w's? Remember we had w1, w2, w3. And then we said, well, that's messy. Let's make it more confusing and concatenate them all together, right? So we can do the same thing for multinomial regression. So this is the flattening I'm talking about. So we can introduce a class-sensitive feature vector, psi of xy. And you could do, just as we described last time, you could take x and repeat it. You could have a bunch of zeros and put x in a particular kind of class location. Review the slides from last time. And w would be one giant concatenated w of size d, which is the original size, and k is the number of classes. So d times k would be the size of the new parameter vector. All right. OK. All right. So any questions on the multinomial? Yeah.
Can we still just find the negative log likelihood?
OK. How do we fit it? Great. So how do we fit this? Yes. Maximum likelihood. So, or minimize negative log likelihood. OK. So we'd have one of these terms for every data point. That's right. You take the log of it, negative log of it, add them over the data points. Yeah. OK. Some more questions on a multinomial? Yeah.
Is there a reason to use the explanation function for the softmax instead of the logistic function? Like use logistic for the binary case and exponential for the...
Oh, right. So is there a reason to do the softmax for multinomial and but in the case, so all right, is the question in the binary case, why do we use logistic instead of multinomial?
No, like, why did you change from logistic to exponential function in the softmax? Like,
Softmax and logistic are one's the bigger brother of the other. So I think you'll find if you look at the softmax for the 2-class case, you should get back logistic regression. Yeah. You might ask, what's the analog of probit for multinomial? That's an interesting question. Some more questions? All right, what's the time? So I have 2 more examples that maybe we don't need to go through now. It's getting a little heavy. We have Poisson regression, where the output space is counts. All right, we have a couple. I'll just quickly show you the pattern. So once again, input is x. We transform it into a linear function of x, w transpose x. And we want to output now the Poisson parameter, which is lambda. Where does lambda live? What kind of value is lambda? What's the domain of lambda for a Poisson? Yeah, lambda is greater than 0, right. So we need f, a transfer function f, to map a real number into something greater than 0. So there's better and worse ideas for this. The standard one is to exponentiate. E to a real is always greater than 0. So that would be our transfer function for Poisson regression. Fit it with maximum likelihood, and that's Poisson regression. Very simple. Once you see the pattern, it's very simple to make things that produce distributions from different parametric families. You can see there's a pattern developing, and there should be a kind of a general version, and there is. The general version is called generalized linear models, and which I have some slides on at the end you can read. I don't know if I'll cover. But there's a kind of a general class of parametric families called the exponential family, and or canonical exponential family. It's a special case that is relevant to generalized linear models. And so Poisson is an instance, Bernoulli is an instance, multinomial is an instance, gamma is an instance, different exponential families that we can do the same game with. And it's the area is called generalized linear models. And the linear refers to the fact that the first thing we do with x is take a linear function of it, and then can transfer it from there to a probability. OK. OK, so that's all the material for today. Any questions on this stuff? OK. So if go ahead and post onto Piazza any questions you might still want to go over related to the exam. And that's it. If you want to pick up your tests, I have them up front.
I have a question. So each of the xi's is like a feature vector. So if there is sparsity, then the conditional probability